Well, thank you so much for including me, and I do love to talk about Federated Wiki. If I jump into a demo, then I kind of get lost showing off things, and I lose track of where I'm going. So forgive me for doing a kind of traditional presentation here. What I really want to talk about, and I think it's a good focus for this idea, especially since there's so many ways to do electronics with computers. What I thought would be a nice thing would be domain-specific languages, and especially thinking of domain-specific languages is really cheap and easy to do, and as kind of a new kind of markup. You know, of course, I'm the guy who said HTML is too complicated, and we ended up with this incredible, six single quotes in a row means something kind of a language. But I've been forgiven for that, and have not changed my ways. So what I want to do is I want to talk about domain-specific languages, and especially with examples with hardware real-time. And so we'll use that. I actually don't do hardware for anything other than fun, and because I have fun with it, I use it as a test case for developing things in Federated Wiki, and getting a good connection with hardware was important for me. Now, I have a little language I call TextZyme. I did it, maybe 3 years ago, 4 years ago. I spent about a year doing it, hanging out with my friends at DorkBot PDX, and it started out as a very tiny and extensible language, and it turned out that tiny was good enough, so I don't do much extension with it. But this book came out, the Domain-Specific Languages, and I did a review of it, really, as kind of a blog post about TextZyme, but I identified what I had done using the names of patterns in this book of patterns, and what I did is I made a delimiter-directed translation with embedded interpretation. And if you get the book, you'll find out what that is, but it's so simple. The other thing is, in the book it says, here are these patterns, and you probably don't want to use them because they'll run out of steam really quickly. And they suggest other patterns you probably move to. And what I like to do is I say, well, what if I make it really simple and figure out a way to not run out of steam? How can I keep it simple and still have value? So here he is saying that first one is you're going to run out of steam, and here's the other one's going to run out of steam, and I'm telling you it didn't run out of steam. So that's pretty neat. What I'm going to show is now 2 years later, 3 years later, I'd kind of given up on TextZyme. I said I've mined that shaft long enough. Let me try something else. But I'm doing the wiki stuff, and I wanted to do hardware again. So of course I hooked wiki up to TextZyme, and that's what I want to show you. And I did it because the wiki has pluggable markup on a paragraph by paragraph basis. So I made a plugin that speaks TextZyme. And it's really kind of another language. Maybe here I'll call it WikiZyme, but I'd like to make it so easy to invent languages that you don't bother to name them. That your language doesn't need a name. So that other language. I brought this hardware. This is a little chip here that'll run TextZyme, and it's got a bunch of different things soldered to it. I like this idea of building things with solder because I can throw it in my backpack and it doesn't break. It's got a thermometer, digital thermometer, a speaker, a character readout, an LED, of course, and then just a bare wire that I can plug into circuit boards and use as kind of like a test instrument. So that's neat, and this is what it looks like. The demo that I'll get to is using this to build an oscilloscope, and the fact that I can build an oscilloscope out of markup is, I think, cool. What would be even cooler, and this is what was really driving me, but I'm not going to demo it today because it's just beginning to work, and this is working with my friend David Turnbull, who builds software-defined radios. This is a radio, little tiny box, makes one of the best radios in the world. It's also really cheap because it's all software. You just load software into it and it becomes some kind of radio. So what I have is I have a little chip that you load software into it. This is sort of like a software-defined peripheral, and TechZyme is how you define it. This is a software-defined radio, and DSP, digital signal processing, is how you define it. And I had imagined that in the wiki, you could just assemble up blocks, and each of these blocks would be a plugin that knew how to do some radio thing. And then you have the discussion on the side that it says, well, here's how we're building this particular radio. Because remember, it can be any radio, but I'll just have a wiki page for any kind of radio you ever want. And it breaks it out block by block, explains how this particular radio works. And then, of course, the oscilloscope. So you bring in these oscilloscope blocks, and you can inspect the behavior of your radio. And I think it's a fabulous idea because radio's gotten very complex. You know, it's not just a frequency anymore. You know, it's a whole modulation schemes and so forth. But that's not what I'm going to do. But think, you know, if what I show you today seems trivial, just imagine next year I'll be doing the radio thing. Last year I got into this new wiki because I wanted to do data, and so here, this was, you know, really the purpose was to do sustainability data that's important to global manufacturers. But of course, the data I had was the sensor data that I've been collecting for years. So one of the first things I did in my new wiki is put sensor data in a little a thumbnail, a little, you know, so there's a whole data set behind that, and it just shows you the most recent value. And that's the temperature in my backyard. And I thought, well, data should be a wiki page that explains it. So, you know, you're getting the idea here that wiki explains itself. But in addition, it's an editor. This is really, you know, I said wiki page should really just be JSON. And what the wiki software does is let you do surgery on that JSON tree to make it into something new. I call this refactoring or editing. And this is the edit history, so that as these things are being passed around, that if I get a page from you, I can see how it got there. And if I mess around with it and give it back to you, you can see what I did because it has that history. Now, when you click that, you can see early versions of the page. But let me digress for a moment and say what I also like about this is when you click a link, it will go find a page that might have different kind of plugins. And here I clicked the page that has a plot. This is, you know, like the beginning, the simplest example of a D3 graphics. But what's neat is it gets the data off this other page. And these don't even have to come from the same server. So I've got this data communication that's happening client side. And now, when you come back here and say, well, where did that data come from? Notice that first edit said that was where I forked the page from another server. And now it's different data, right? I have data that I'm pulling off a server. I move it around into other wikis. Now when I call up this same graph, so now I have the graph page, the D3 line, brought up twice, and it just goes and looks for the closest data set, so it plots it. And I think of this as a lot like the Unix command line, where you pipe things together, and you know, this thing that's reading data is going to read from whatever's being written to the left of it. You know, it's sort of a wiring model, but without the wires. Just put things next to each other, and that's something that I live with, and I try to figure out how it works. So that's the background. Now let me go into TechZyme itself, and I'll show you how I built the plugin in this environment. And we got to start with wires. This is looking at a wire from inside the chip. This is the chip looking towards the outside, and what can a chip do to a wire? And a lot of times you use this kind of fluid model for electricity. Think of it as water, and here we're sourcing some current out that wire. You know, this is driving electrons out. Here we're in essentially sinking current electrons from the wire, and dropping them down on the ground, and they'll eventually get around and come back again somehow. Or we can just plug up that wire and do nothing with it, in which case whatever happening outside, we can tell what's happening, but we're not influencing what's happening outside the chip at all. Now, in TechZime, I have one-letter commands. And here I have a command O says output something. And it's going to source current because I say output a 1. The 1 is a command. It says set. I have one variable, and I don't even name it. Well, actually, inside it's called X because I thought I might have a Y and Z, but it doesn't even show. If you only have one variable, you never have to name it. So it says load the variable with 1 and output it. Now, this was remind me to talk about Martin Fowler and DSLs. This is the ghost of Martin Fowler there, and the thing is, remember, actually I'm going to skip that part. I think that actually came up too early. So here's another one. Ignore Martin there. A 0-0 means sync current. Oops. I'm getting nervous. And then finally, the command for plugging it up is you say input. And remember, you can tell what's happening. And of course, if you read what's happening, you need to do something with it. So I have a command called P, which prints the value of what it got, and that just sends it back to some host computer. So I can drive signals. Here's what it looks like in my interpreter, because I have a little interpreter in here, and so it's just a case statement. It says when you see an O, do a digital write. When you see another O, it's the same digital write, same command. When you see an I, do a digital read, and when you see a P, print it up. Here it says serial, but think of that as USB. It's a USB with a serial protocol. And I'm arguing that this is simple. The next thing I have to think about is time, because everything happens in time. So here what we're going to do is watch a signal come out of this pin, and we want to know, well, so there's obviously a 1-0 and a 0-0, and that time in between is I say, well, do 100 microseconds. And 100 microseconds, each character the interpreter takes about 10 microseconds just to do the case statement or switch statement and do the command. So time is passing just as you're doing those characters, but if you want more time to pass, you can do that. And so the 100 microseconds is between the U and the next 0, which means that pulse is going to be like 160 microseconds. But I just live with that. It irks some of the people who use this stuff that I say 100 to get 160. But, I just count the number of letters and multiply by 10 to get a pretty good approximation of time. And this, in my case statement, actually gets kind of complicated because the package I use would slip into floating point, and that takes, 1,000 microseconds to do the floating point on an 8-bit processor. So I took it apart. That complicated operation all gets done by the compiler, so it's really just a small integer multiply to take the internal register and figure out how many microseconds. So now I got to show the example, and of course you always start by blinking an LED, and I've just proven I could get Keynote to blink an LED. So now let's see what it takes to use TechZime to blink an LED. Because this is just on a USB cable and the USB shows up on the device, I could type this command at the shell, and what I'm doing is I'm saying output a 1, wait 500 milliseconds, output a 0, wait 500 milliseconds, and repeat that 10 times. That'll make this LED blink. And I've picked up some extra stuff like the echo and the redirect to /dev and so forth, but that's the operational part. And here I've changed microseconds to milliseconds so that it's long enough you can see it. Here's the milliseconds case is pretty simple. Then I have this command called right curly bracket that says decrement the count, which started at 10, And if you haven't counted down to 0 yet, just jump back to where that left arrow was. So super simple control structure, but it lets me write something. In fact, here you can see this is the whole loop. This is what Martin Fowler said is so simple you probably don't want to do it, and I think it's so simple you probably do want to do it. You know, I've kind of grabbed all the pieces now out here a little bit at a time of the TextIme interpreter, and you can see this is an idiom. The first line, you know, in the earliest guys building computers, they called this the fetch execute loop. What I called buff, they would have called the program counter, and what I called ch, which is the character, they would have called the instruction register, and that's how they build computers. And you know, only now we're kind of getting away from that. That's called the von Neumann bottleneck. So anyway, the thing that really makes this work and be neat is actually this wire, this USB cable, because I've described from the part looking out and made that really simple. But there's a lot going on here, which I just inherit, and that's because I've got this CPU. You know, it's $10 or something. You know, it's not expensive, but you know, it's a nice machine, and it has hardware in the chip for doing the USB protocol. And so what I do is I have my laptop hooked to the USB, and that's how I deliver these programs. Here's a bunch of programs coming down to the chip, and they're coming down as lines. This thing processes a line at a time. And if there happen to be P commands in this, after spraying out some bits, it would send values back up. So this is a two-way connection, and it's flow controlled. So I can write scripts that will pipe stuff down to this, and the laptop, whether I'm running Perl or JavaScript or whatever up on the laptop, it's all sequenced by these timing instructions, microseconds, milliseconds, down in the chip, and the laptop isn't that good at precise timing, but it all works out well that way. So that's how it works with Shell, and like I said, I spent a year writing that kind of stuff. Here I'm going to show you how you can get stuff back the other way. If I want to get stuff back the other way, I need another command here. This time I'm catting from the device, and I just detach that. So that's in the background. I have actually two Unix things going here. And if I do that, because I put the word blink, and my quote character here is underscore, that way I don't interfere with the quote conventions of the shell. I didn't want to use quote or double quote, because then I would have to figure out how to quote a double quote or something. And when I run this, you know, there I am. I'm blinking, and so that's cool. So now let's get up to federated wiki, because that's what I know you're here to hear about. Here's the way we did it in the shell. Here's the way we do it in federated wiki. So what I did is I came up with this second language, which is also very simple, and I just said in that language everything will be uppercase. So if it's uppercase, it's a language that's interpreted by federated wiki in a plugin as a new kind of wiki markup, and it's a markup for controlling, for basically replacing echo and the /dev and all that stuff to make it easy to do TextIme. But the operative point in this is the same code. You know, it's just turn a bit on, wait 500 milliseconds, turn it off. What I do, though, here is I say, in federated wiki, I say, you know, you can use browser-based timing things, set interval, and figure out how to run this, you know, once a second. So I don't even have to write the loop here, because federated wiki understands in my world that I do things every second or every minute or every time the mouse moves or stuff like that, all this event-oriented stuff that's in the world of the browser. And here's what it looks like. Now this time we're in browser code, and it says, well, trigger is a little function which says you've got a bunch of definitions. it's time to start executing the definition called second. And by the way, there's a set of arguments, which is the number of seconds and minutes and hours of the time of day clock. And so here's what I've really done. I've taken this model and I've inserted a federated wiki server. I call it, the Node server. This is a pattern I think we're going to see a lot of. This is the add a Node server to your system pattern, or we'll call that Node server injection is the pattern. And this is so I have this plugin that talks to the Node server as if it was talking to this device, and then the Node server just relays it both directions. And again, all the buffering just works out great. So, and you can guess what the code is there. I have to tell you, I like to program things the hard way, just so I know what hard is, so I can really appreciate how simple it can be. And I want to thank Nick's over there. Nick's very gentle with me. He says, you could do that a lot easier, because I'm doing all these incomplete reads and all that. And we finally get it down to duplex stream, which is another famous pattern. Thank you for that. Anyway, now I have to peek ahead. The question is, what's the big deal out of this? So I have these different markups. I claim they're simple, but how do you make something cool? And now I have to tell you a little more about federated wiki. We're going to step back a little farther and say, in a traditional wiki, we basically took a disk full of documents and we made it editable by the world by putting a web interface on it. We're sharing among different people by sharing one disk. And what federated wiki does is it turns that kind of upside down. It says, we're going to have a bunch of disks. Everybody brings their own disk space, and the sharing happens in the terminal. So the browser, I guess. And that's because we now have a great environment in the browser, and this isn't that much different than the original plan for the internet, except what I do is I bring the pages up in the same tab and let them talk to each other. So this idea that the pages aren't isolated in their own tabs, they're all in the same tab, and I let them talk to each other. And so I think that's pretty original. It also makes it feel like a wiki, even though everybody's really writing in their own space. Now, I do that for a variety of reasons, but it opens up the opportunity to use that, server to do something new, to establish new kinds of connections. And what I'm doing here is I'm looking for a low latency connection, so I use WebSockets, kind of alongside the HTTP requests that you would expect of a wiki. And then, using that duplex stream, I'm hooking up my chip. And it's really nothing more than that. The way I manage it, however, is I have these little plugins where when you say this paragraph is of type image, it puts an image. If you say this paragraph is of type TextZyme, it puts this TextZyme interpreter. And the TextZyme interpreter has two halves. One half goes on the server. Down there is that little gray box. The other half goes up on the page. And so these two halves, are the same author. They can decide to talk any way they want. And so I just do WebSockets as a demo because it's a cool thing to do. But what's really important is when the server starts, it starts up that server-side component, and whenever anybody goes to a page that has a paragraph of that type, it fires up the client-side component, and they find a way to work. This is also called the half-object plus protocol pattern, because I have two halves of what I think of as one object, and I have a protocol between them that is of the design of those half objects. So pattern that was used a lot in telephone switches for the half call. You get a half a call, and when the guy answers, you get a full call, and either person can hang up because they've got a protocol between them that distributes your phone call object across multiple digital switches. The other thing is if I open another page on another server, I can down here in the Node server, I can manage lots of these conversations, so it's got nice sharing potential. Once again, here's the ghost of Martin Fowler. The reason why I think this is important for DSLs is that the JSON that I'm moving back and forth is inert. I can read anybody's JSON and not be afraid of it. I can't read anybody's JavaScript and run it without being afraid. People are working on that. There are systems of sandboxing JavaScript. But what I do instead is I say, well, I'll just send these scripts in DSL, and if I don't have the server-side component loaded, I know it's not going to run. I can protect my server from something that's a kind of suspicious markup by just not having it. But if I'm behind a firewall and want to have lots of really powerful scripts, I can have more powerful plugins on my server, or I can design scripts that are just sufficient for doing something that I want people to be able to do, and balance it out. So lots of little simple languages is a good idea. Let me show you what this looks like when it boots up. Here it is starting the server. Actually, it wasn't quite this pretty. I just edited it to make it look really pretty. Maybe I'll make it look like this. So here the server's coming up, and it just says, oh, I found some plugins that have server-side parts, and I'll fire them up, and then they just start listening on these other WebSocket addresses. And so that's because that's the only thing I do at the moment is a WebSocket. But that gives you the idea that on startup, that's pretty simple. Here's what it looks like starting up the client side. I just go to a page. Unfortunately, the little plugin is a little further down, so you don't see it, but it just renders this little gray box, and we'll see some more in a minute. And these, are unrelated in time. Let's do an application. And now I want to go back to that electronics, the ins and outs. What I do is I'll take apart, here I have this display that just happened to fit on here. I just soldered in, fit beautifully, but I had to go read the data sheet, and I pulled out this stuff. Let me show you what the little processor chip. See, so look at how the pins, the power and ground just happened to match. Now I had to actually turn the chip upside down to make it match. But basically, the way I start programming is I say, well, what am I supposed to do to this chip? And here's the wiring diagram and the chart. Let's start with that bottom one. It says clock, and so that says clear. So if we want to do a clear, I say let's define a function called clear, and I see that in my simple language, if you put a name and then some texime, you're defining that name to be that texime. So I'm saying, here's how to do a clear. Clear came from that pin, and the number there says, oh, that name is associated with pin 7 of port F, and it's a little blurry, but that's actually how it's printed on the part. So that if you hook a wire up to the part, it's got that name right there, and so you know what to type. Then it says, well, when we want to clear the part, we go low. We start sucking charge out of the wire, so that's a 0-0. We're going to output a 0. Then down here, it says the clear takes 10 microseconds, and so I put in 10 microseconds, and then I've taken care of that. So I've taken care of one thing, the write command that actually writes into one of these characters. That's similar, and everything else in this chart is in nanoseconds, and so I know that it takes 10 microseconds for every command. So I'm never going to go faster than that. So I just stop worrying about time. I just worry about the sequence in there. So this is kind of defining what the basic operations are. Now the part, it turns out when you write to the part, you address a character. There's 4 characters, and then you set the data, which is just the ASCII for whatever character. So here's commands that'll do the address and data, and so address is that set of pins. Those 2 pins make for an address of 4. and that's at pin 0 and pin 1 of the F register. Now this B0 and B1 I'll get to in just a second, but let me just say that when I put all this in, I've taken care of both the address and now taken care of the data, which is 7 bits worth of I/O. So I pretty much, and there's one more and it's blurry and I skipped it anyway, but there it is. So now my application, to test this, I'm going to put in kind of time here, so I need a colon. So here's what it looks like. I define a function called colon. It says address character positions 2, and that slash notation, that says expand the ADR, the address macro, and the argument is the number 2. And so when I say B0 and B1, that's talking about bit 0 and bit 1 out of whatever that argument is. So those will turn into zeros or 1, and so I output zeros or 1. Simple language. Here I have the ASCII for the colon, and that goes to all those other B's in the second line. So let's see if we can run this code. And what I'll do is I have this. Every plugin has documentation, which is also in Wiki. So I'll say here it explains all these commands like seconds and hours and minutes and whatever, but it also has some examples. So let's go look at the examples. And one of the examples is the HDLX 2416 display. And when I pick this up, it just lights it up. Can you see that this is lit up? And it turns out, as I double click this, I can see the markup here. This is, there's a little more going on here than I showed in my thing, but it just says every second display a tick, and a tick is, addressing and characters and so forth. So this is, and here's that colon thing where I output a colon, and those bits, and, it's right in there. So this is a complete program to light up this, and what it's doing is it runs once a second, and it puts the number of seconds. If you could see my clock up there, you would see that it matches it exactly. And this is kind of a complicated part. So to be able to derive this part with wiki markup is a bit of a challenge. Now, down here, and let's see, I just learned how to do this. Let's see if I can make this work. If I zoom in, down here, as it runs, it tells you every time it sends a request down to here, and if anything came back, it would tell me that too. I also have this ability to kind of thumb through data, and as I do that, it turns out it's blinking this one last digit, scrolling through. And if we look down here, we've already sent down 212. So this is really to test that low latency stuff, and it works great. Let me see if I can get it all on the screen. What I didn't realize is when I do this magnify, everything will be moving back and forth. Maybe that's not such a good presentation. Well, maybe it'll get us all kind of, dizzy. So complicated part captured in markup. Now I want to do something that's a little simpler part, and I think that it's a little simpler part, but I'm doing a more complicated thing. And that is, I got a little speaker on here, and if I want to talk to the speaker, what I'm really going to do is I'm going to shoot some ones and zeros out to that speaker, and of course I'll do that by outputting a 1 and output a 0, and that'll make a tone. And if you find this online, you can see how I taught it to send Morse code, dee 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 dee, because that's just tones. But what I do here that I think is more interesting is after I put a little burst into that speaker, what I do is I stop sourcing and syncing current and go into that tri-state, into that third state of just listening, and the speaker crystal, this little piezoelectric speaker. It can be a microphone too, and it's still bouncing. It's ringing like a bell, and the wave will do that. And so now I have one new command called S. S is for sampling. That'll read that same pin with an A to D converter, and then of course once I read it, I print it, and so that sends these samples back up through this chip, back up the USB, back up the WebSocket, all the way to the browser. So that's my next demo, and so we'll see that. And here what I'll do is I'll just say, well, forget about this other thing, so I just reload the page. That kills the other job. I call this the TextZime oscilloscope, and here it is running. Let's see if you can hear this. I got a microphone here somewhere. Well, this worked just well enough that, so it's clicking. And of course it does it once a second because the program I wrote here says to do it once a second. And there it is. It says every second output a pulse and then sample, and here's how I said to do a pulse, and here's how I said to do a sample. And so it just works. Now, if I look closely at this, and let's try the close button again. Oh, wrong button. How about this one? There we go. So you can see that every time I send, every second, I get 60 messages back for those 60 Ps because I put it inside a 60 repeat loop. And if I want to see what that actually is, I can just let's see, how do I get over there? Well, if I just tap that, then here I'm magnifying it, and you can see all the numbers. It just captured the 60 numbers, and they're changing back and forth. There it is. So that's pretty cool. And my program was, I just say do a bunch of Ps, and then this thing on the client side, it just catches them and puts them in an array. Now, we're out of time? Well, great. I am almost done. And what? It's just lunch or something? So the cool thing I can do now is it says, well, why don't you try that D3 line? And this is the same thing I did 2 years ago to do the temperature in my backyard. Is now looking at my the ringing of this bell and animating every second I get a new set of data. And what I love about this is this is a general output routine hooked to a general input routine, and I just put them next to each other, and they get hooked up. So I'm going to finish here in seconds by just making some observations. I call this takeaways, and this is what you should have learned here. First of all, this is about sharing in a wiki and doing in a wiki. This is a wiki where you can actually go to do things instead of just talk about doing things. It's also about DSLs to give life to plain text. Plain text in a wiki through these markups can become alive. I think this is actually more agile than Agile, and since I'm got that Agile stuff started, I can say that. It's very dynamic. It's dynamic in the same way the command line was dynamic. And I know that what I'm doing is a tiny little thing, but it's just filled with potential. Of course, I'm humbled by Max watching what he does, but this is such a great time for thinking big, and I think this is big for Wiki, and of course Node is big for everything. So thank you very much for your attention, and let me run over just a little bit.